Let's try this. Okay, so in my infinite wisdom, you guys can't see my face, but I'm making a face. I thought it would be a good idea to run through this first activity in chapter 9 together, so that you guys can kind of see what it's asking and I can discuss each thing individually. So, activity 1 in chapter 9 is found on page 247. And it's got several exposure factors and their associated changes, and then it has a table that is asking you to determine whether or not that's going to create an increase or decrease, or no change to the exposure to the IR, the contrast, and the spatial resolution. I used my whiteboard and I went ahead and set it up ahead of time. It doesn't look like I really planned it out, but just trust me, I did. And I went ahead and filled in across the top the change that we're dealing with. So, of course, down here I'll write what the table says. Your exposure to your IR, contrast, and spatial resolution. Your activity gives you a set of exposure factors. We've got 200 MA, 50 milliseconds. You can make a, excuse me, a quick little mental note to yourself that that is 10 MAS overall. We got 70 kVp, a 40-inch SID, a 0.6 millimeter small focal spot size. We're using a 12:1 grid, a CR image receptor. I didn't even realize that was there when I practiced this a while ago. 8 by 12-inch collimation. The patient's thickness is measured at 10 centimeters, and we have minimal OID for our projection of the hip, it says that we're doing here. So the changes we're going to have are going to go over here, and then we'll determine whether or not that's going to create an increase, decrease, or no change to the exposure. Let me see. In the textbook, it says to use a plus sign to signify an increase, a minus sign to signify a decrease, or put a 0 if there is no change. So the first thing says that we're going to go to an 85 kVp. 85 kVp. We started with 70 kVp, so this is an increase. If we increase the kVp in any situation, now this thing is saying that it's without making the compensating changes. We're not going to say, well, if you would increase the kVp, you would decrease the MAS to maintain exposure. We're not doing that here. We're just talking about if you were to make this change, period, what would happen. If we increase our kVp, we're going to have an increase in the exposure to the IR. Remember that kVp increases not only the penetrating power of the beam, but also the number of photons in the beam itself. So we'll have an increase there. We know that we're going to have a decrease to our contrast, because when we use a higher kVp, we get a lower scale of contrast. We get low contrast. That's long scale contrast with lots of grays. And as far as spatial resolution is concerned, we're not going to have a change. There's no change in spatial resolution. The only things that change spatial resolution are geometric things like your focal spot size, your OID, SID, those kind of things. If it's not a change in the geometry of the setup, it doesn't change spatial resolution. So put a 0 there. All right. Next, it says we're going to use a 1.25 millimeter, that says millimeter, just trust me, focal spot size. This one is also an increase. That's a large focal spot compared to what we used before. So if we increase the size of the area on the anode that's getting hit with electrons, is that going to change anything as far as our exposure to our IR? No, it is not. No change. Your exposure to your IR is not determined by your focal spot size. Is it going to change the mix of the energies that constitute our contrast? Also a no. No change there. Finally, though, we do see that it does create a change in the spatial resolution. Focal spot size is your primary controlling factor for spatial resolution. If you use a larger focal spot size, you are going to have a decrease in your spatial resolution. That is crooked, but it'll do. Okay, Next, we go to a 45-inch SID. This is harder to write on than I thought it would be. That is going to be an increase in the SID. If we have an increase in our SID and we don't change anything, what do you think is going to happen to the exposure to the IR? It is going to be decreased. We will not have as many photons striking the image receptor, because remember that as you increase the distance, you allow the beam to diverge more, so it spreads out more, so you can't, you're not exposing the same amount of space. It would be a bigger space, so it wouldn't be equal to what it was before. The contrast. Changing your distance changes the number of photons that reach the image receptor, but does it change the mix of the energies? No, it does not. No change to contrast when you change your SID. Last but not least, spatial resolution. I can't talk. If you increase your SID, you are going to have an increase in your spatial resolution. Remember, your ideal situation is to have the longest SID, the shortest OID, and the smallest focal spot for your spatial resolution to be improved. So if you have a longer SID, you're going to have an increase in your spatial resolution. All right, next we have 50 MAS at 0.2 seconds. If you math that, that is also 10 MAS. So it's no change here. Circle, we'll do a circle. No change with that. So is that going to change your exposure to your IR? Nope. Does MAS have anything to do with contrast anyways? Nope. And does MAS have anything to do with spatial resolution? Also a big negative. Nope, nope, and nope. Easy peasy. Patient thickness. We're going from 10 centimeter thickness to a 6 centimeter thickness. That is a decrease. If the patient is not as thick and we don't change our technique, what's going to happen to the exposure to the IR? It's going to increase. So we have less stuff to attenuate. Contrast. We know that contrast is decreased whenever you have an increase in patient thickness. In this situation, we got the opposite. We got a decrease in the thickness, so we're going to have an increase in the contrast. And your decreased patient thickness kind of acts like OID. If you have less thickness, then the patient's parts are going to be closer to the image receptor, so you will have an increase in spatial resolution here as well. You can see that if we would just X-ray only skinny people, we would have fantastic images, right? You would have an increase in all the factors if you decreased your patient thickness. All right, our next thing says we're going to use no grid. Remove the grid. No grid. That is a decrease in grid ratio, going from using a 12-to-1 grid to using nothing to nothing grid is going to make some changes. So if you had that grid there to stop those extra photons before they struck the image receptor and you took it away, then what do you think is going to happen to your exposure to the IR? It's going to increase because you don't have something there to stop those scattered photons. What about if you do the same thing? What's going to happen to your contrast? If you had a grid there to stop the photons, the scatter photons, and then now they can get there, so you have more scatter. Scatter destroys your contrast, so you're going to have less contrast. And then spatial resolution, no change. The grid doesn't change the geometry of the situation. It will increase or decrease the visibility, but it doesn't do anything to the accuracy of the recorded detail. Remember that your spatial resolution goes along with your accuracy of recorded lines. Oh, I think I just realized I didn't have enough spots here. Ah, crap. Put another spot. Oh, God. Oh, God. That's terrible. We're going to make it work, though. Okay. We're going to increase, the next thing that says is that we're going to increase the OID to 4 inches. It said on our starting out thing that we had a minimal OID. So we've gone to a 4-inch OID, I can't write. That is an increase in OID. So if we have more space between the patient and the image receptor, what do we think that's going to do to our exposure to our IR? Your chapter on scatter control explains to you the air gap technique. For the air gap technique, it's ideal that you use a 10 to 15 centimeter air gap. But anytime that you have an air gap, you have that opportunity for scattered photons to not strike your image receptor. And that's what we'd have here. So if you had more space and that space allowed the photons to spread before they hit the IR, then we would have a decrease in the exposure to the IR. As far as the contrast is concerned, the same thing with that OID that allows the scatter to miss the image receptor. So going to increase your contrast. It's going to make it prettier because you're not going to have all that off-center, off-focus stuff. And then the OID it's a geometric thing, so it is going to affect your spatial resolution. If you have more OID, the edges of your part that you're trying to radiograph are not going to be as crisp, so you're going to have a decrease in the spatial resolution. Okay, the last thing, which I almost forgot, is a 14 by 17 collimation. That is an increase in our setup. The problem said that we had an 8 by 12 inch collimation. This is working on the premise that we talked about with scatter control, also about the volume of tissue irradiated. So volume of tissue is made up of patient thickness and your field size. So if you increase your field size, if you're actually exposing a bigger area on your image receptor, then you're going to have an increase in the exposure to the image receptor. Recall that the lead shutters in the collimator box work by photoelectric effect. And if they're open, then they're not stopping as many photons. So more photons are getting out, more exposure to the IR. Okay, same thing, only different. If you increase the increase the area, you have decreased your collimation. Are you going to have more or less contrast? You're going to have a decrease in contrast because this increased field size allows for more scattered photons. And recall that the scattered photons are going to grade your image contrast. And then last but not least, on your collimation, if you change your collimation, is that going to do anything to your spatial resolution? Is it changing how far away it is? Is it changing the lineup of stuff? Is it changing SID, OID, what else? Focal spot size? No, not changing those things. So it doesn't change. Oh, that's really terrible. Oh, well. It doesn't change your spatial resolution either. So hopefully you guys understand that. These are important concepts for you to understand for your next exam. And I feel like in life in general, but hopefully these will help. I do want to point out to you guys, there are a lot of activities in Chapter 9. The film activities are not necessary to do. I'm not going to test you on those. Some of it is material that we haven't covered because you don't have to know it. But also I want to point out that there is an appendix at the end of the book that has these answer keys worked out so that you can do them. Definitely do them on your own and then check yourself. Don't just look at the back and say, oh yeah, I'll read over this and it makes sense. That does not do the same thing in your brain. So don't just do that. I'll do a couple more of these, but I just wanted to do this one first so that you guys could get a feel for how that would go. Hopefully it helped. We shall see.